Okay, so parabolas and their graphs. In this lecture, we'll be talking about parabolas and their features, graphs of parabolas. So the basic parabola is this. This is its graph, y equals x squared. Domain, any number can be squared, so the domain is all reals, or minus infinity to infinity, if you want to put that into interval notation. Vertex, that's the point at the bottom, 0, 0. The range is y values. So this is a graph that has a bottom. The lowest point is y equals 0, has y coordinate y equals 0, so the range is y greater than or equal to 0. The axis of symmetry, well, parabolas are symmetric around wherever the vertex is. So the axis of symmetry here is x equals 0. And there's three special points, 1, 1, 0, 0, and minus 1, 1. Those are the three special points on a graph. They help us when we're trying to look at stretching factors, knowing where those are. So all parabolas are variations on this basic parabola. In class last time, we talked about moving the parabola left and right by replacing x by x minus h, right? If h is positive. If h is increasing, it moves to the right. If h is decreasing, it moves to the left. Note that there's a minus sign there. Moving up and down by replacing y by y minus k. K is positive, it goes up. K is negative, it goes down. Right? Another way to change a parabola is to rescale it. So hopefully my video editing skills work here, and I can splice in a little video about scaling factor. If not, it'll be posted as a separate video. So this is the graph of y equals x squared. What we want to talk a little bit about is what's a stretching factor and what does it do to this graph. So I'm going to put in 3 basic points, which will be very useful for dealing with our graph. And that's those 3 points, A, B, and C. And this is minus 1, 1, and this is 1, 1. I'm going to change these colors to make them red, because they're going to be tied to this graph. So I don't need a label, but I just want to make them red. Okay. So there's our parabola, basic parabola, y equals x squared, goes to the point 1, 1, goes to the point minus 1, 1. So as we saw before, you can put in sliders in GeoGebra. And there's y equals x squared in black. With a equals 1, it's just the same parabola that we had before, so it exactly overlays it. I want to add to this the point 1, f of 1. And there's that point D on the graph. And I want to add the point minus 1, comma, f of minus 1, which is this point E on the graph. So there's our black graph. That's the graph of y equals x squared. So A is a scaling factor. If I make A bigger, what happens to the graph? It should get bigger, and E and D should actually be going with that. Except these should be G's and not F's. Sorry about that. F is the actual regional parabola. There we go. That's better. So when A is 1, we have this. As A increases, what happens? Well, it looks like the graph is getting narrower. And if we make A get smaller, the graph is sort of getting wider. And when we get to 0, well, anything times 0, if I can actually get it exactly to 0, 0 times x squared is 0, so we just get a horizontal line. It's hard to get it to stay there. There you go. And if A is negative, it's flipped over the x-axis. So when A is minus 1, my y values have become negative. So the scaling factor does 2 things. It stretches the graph, and it also flips it over the x-axis. If it's negative, it flips it over the x-axis, so your graph opens down. If it's positive, the graph opens up. So let's set A equal to 4 and ask ourselves, well, what's really happening here? Is the graph getting narrower or not? Well, E and D are these 2 points, the red points, but with the scaling factor of 4. And so what happens is, as we change the scaling factor, E and D don't change their x-coordinate, they just change their y-coordinate. And if the scaling factor is 4, that means the height they are above the x-axis is 4 times what it was from the basic red y equals x squared graph. So D, for example, when y is 1, it is, there we go, close enough. When y is 1, it is 1 unit above the x-axis. When a is 2, it's 2 units above the a-axis. When a is 3, it's 3 units above the a-axis, above the x-axis. So the scaling factor, what it's doing is actually pulling E and D upwards, and that makes the graph narrower. And you can tell how far it is because on the basic graph, y equals x squared, if you go 1 unit from the vertex and 1 unit up, then you get back onto the graph. But if you've been stretched by a factor of, say, 3, if you go 1 unit to the right, you go 3 more units to get to the graph. If you're stretched by, say, 0.3, instead of going up 1 unit, you go up only 0.3 of a unit, which means that the graph is kind of wider because E and D now have been pulled down a little bit from the x-axis, from the original parabola. And then finally, if a is negative, your graph has been flipped over the x-axis and may have been stretched a little bit. So if a is -2, your graph has been flipped over the x-axis because a is negative, and it's been stretched so that this distance here is 2 units instead of the 1 unit that you have for the original graph.
Having seen the scaling factor video, what's the scaling factor of this parabola below? Well, there's the vertex. We go 1 unit to the right. How far down do we have to go to get back onto the graph? We went down 3 units. Going down means that it's negative scaling factor, and it's been rescaled by a factor of 3. So this is y equals -3x squared. We took our original graph, we multiplied it by -3, and that rescaled it. Okay, so the standard formula for a parabola then is this formula: y equals ax minus h squared plus k. So, had a little interruption there. Hopefully we can just stitch things together. So the standard form of parabola is y equals ax minus h squared plus k. H comma k, that's the coordinates of my vertex, and a is the stretching factor. Stretching factor. So, use transformations. That's what my math lab, that's the language my math lab uses. But basically we have this graph. We want to be able to figure out what does the graph of that thing look like. We know what the vertex is. It's 3, 4, because this is h. That's k. The stretching factor is -2. That's the thing out front. So what does that tell me about this graph? Well, its vertex 1, 2, 3, 1, 2 is here. Stretching factor of -2, that means it's going to be opening down because of the minus sign. And if I go 1 unit to the right, I should go down 2 units to get to those special points. So there's my graph of my parabola. Just something like that. Right, and when it says sketch, it's a freehand graph. We're not expecting, fabulous art here. So the axis of symmetry is x equals 3. It's a vertical line that goes through the vertex. The domain for parabolas is always all x. The range, now this is a graph that's got a top. So the range is all y's that are less than or equal to 4. How do you find the y-intercept? Set x equal to 0, solve for y. So our equation is this: 0 equals, set x equal to 0, so -2, 0 minus 3, quantity squared plus 4. This becomes -2 times -3, quantity squared plus 4. Remember your order of operations. We do the squaring first, so -3 times -3 is 9, times -2 is -18, plus 4 equals 14. So that's my y-intercept. It'll be way down here somewhere. What are the x-intercepts? Set y equal to 0, solve for x, right? Now we're looking for these 2 points. So So 0 equals minus 2x minus 3 squared plus 4. Subtract the 4 from both sides. And then you can divide by the minus 2. Minus 4 divided by minus 2 is just 2. X minus 3 squared. How do I get rid of a square? Take the square root of both sides. Remember that when you take the square root of a number, like 2, throw a plus or minus in front of it. X minus 3, and then we get 3 plus or minus square root of 2 equals x. So note a couple of things about this. One, there's the axis of symmetry. It goes through the vertex. It's also halfway between the two roots. This part is the x-coordinate of the vertex, the 3. The plus or minus 2 is how far you go to the right or the left of the axis of symmetry to get to your actual root. So the graph at this point is essentially 2 times square root of 2 units wide at that point along the x-axis. So the vertex, x-coordinate of the vertex is halfway between the two x-intercepts. Okay, so here's another one. Here's a parabola. What's the formula of this parabola? Well, the formula that we want, I'll write it down here. The standard formula is y equals a x minus h squared plus k. H comma k are the coordinates of my vertex. A is the scaling factor. So if I can find the vertex and the scaling factor, then I can write down the formula for the graph. So the vertex is at minus 1, 1. The scaling factor, I have to be a little bit careful here. 1 unit to the right. And then how far up do I go to get back on the graph? 1, 2, 3 units to get back up on the graph. So the scaling factor is 3. So what's my formula? Scaling factor is 3 times x minus minus 1. So that's going to be an x plus 1 squared plus 1. So there's my formula. Domain, all x. Range, well, here y equals 1 is the bottom of the graph. So the range is y greater than 1. And we can see y equals 4 is where the y-intercept is. So finally, what are the x-intercepts? There are none. It doesn't go through the x-axis. Its vertex is above the x-axis, and it opens up. Well, what happens if we try and solve this? What happens if we do the algebra? Well, we set y equal to 0, and 3x plus 1 squared plus 1. Subtract a 1 from both sides. Divide by 3 to isolate our squared term. Take the square root of both sides. And subtract a 1. So if we actually just grind through it, we get this. And there's a problem. We have a negative number inside our square root. So no x-intercepts. We get this negative square root. There is, in fact, a way we can deal with that, and we'll talk about that in the next lecture.